Hello APC Mechanics students, today we'll solve the past paper of RQ 2013 exercise number 3. A disk, so always remember that the figure appears above the text. A disk of mass m is 2 kg and radius r is 0.10 meters is supported by a rope of negligible mass. As shown in figure above, the rope is attached to the ceiling at one end and passes under the disk. The other end of the rope is pulled upward with the force Fa. The rotational inertia of the disk around its center is given by mr squared divided by 2. Now the pulley or the disc has inertia, which means that the tension at both ends is not transmitted equally if and only if the disc is at equilibrium. Now basically we're starting at equilibrium because in part A they're telling us calculate the magnitude of the force Fa necessary to hold the disc at rest. If the disc at rest, which means the tension here is equal to the tension here, and we know that the force can be determined using Newton's second law. Or we can simply say what are the forces acting on the block. We have Fa here and Fa here, and we have the pull of gravity down, which means that Fa plus Fa would be equal to the pull of gravity, and the reason is given by balance forces. Then the double of Fa is Fg, which means that Fa is Fg divided by 2, and Fg is mg. The mass is given by 2, g is given by 9.81 divided by 2. Then the force Fa is given by 9.81 in newtons. This is it for part A. Now after that they're telling us at time t is equal to 0 the force Fa is increased to 12 newtons. Then 12 newtons is enough to start lifting the disc up, causing the disc to accelerate upward. The rope does not slip on the disc as the disc rotates. So here, because we don't have slipping, and the disc will perform two types of motion, translational and rotational, then both variables of motion can be related. In part B, they're asking us to calculate the linear acceleration of the disc, and this is done by utilizing Newton's second law for both types of motion. Let me start. So here, let me indicate what's happening. Now here we have Fa along this part of the rope. Now at the other part we would have another tension force, which is given by Ft. Now it's not important for us to draw an FBD, but I will represent them here, and we have the pull of gravity down, which is given by mg. Now why I have represented the tension to be less in magnitude to Fa, because the inertia of the disc will be I mean, if you think about it, there should be unbalanced torques in order to produce torque or acceleration upward. For this reason, Fa would be greater than the tension. Alright, so now let me start by applying Newton's second law for translation. Now here what do we have? We have that F naught is equal to ma. What are the different forces acting on the disc? We have the pull of gravity plus the tension force plus Fa on the right rope is given by ma. Now we need to project this. Our positive direction would be up because it's accelerating up, so I will say projection along the vertical. The pull of gravity is down, so that would be minus mg plus the tension plus Fa is given by ma. Now here we know what is Fa. Fa is given by 12 newtons. So in order to calculate the linear acceleration, and notice that they told us calculate, not derive, so we need to determine the numerical value. We need to find the tension, and this can be determined again by referring to Newton's second law, but now for rotation. Then let me say again, apply Newton's second law. Which states that torque net is equal to I multiplied by alpha. Now, what are the two forces that are producing torque? Here notice that we don't have any pivot, and the pull of gravity doesn't produce torque because we're producing torque around the center. So we would have Fa and Ft, and these are applied tangentially, so no need for a cosine or sine. So that would be Fa multiplied by r minus Ft multiplied by r is equal to the rotational inertia, which is given by mr squared divided by 2 multiplied by alpha, but we have stated previously that we have motion which is rolling without slipping, then alpha can be related to a by a divided by r, because we need to make use of the cancellation effect here and here as well for these. Then Fa minus Ft is given by m divided by 2 multiplied by a, and the tension in this case would be given by Fa minus m divided by 2 multiplied by a. Now this tension would be replaced here, so we have minus mg plus Fa minus m over 2 multiplied by a plus Fa is equal to ma. Now we can move this to the other side and we read the equation from right to left. That would be 3 over 2 ma is given by the double of Fa minus mg, and the acceleration in this case is given by the double of Fa minus mg divided by 3 over 2m. Now Fa is given by 12, the mass is given by 2, g is 9.81, and 3 over 2 multiplied by the mass, which is 2. Plugging this expression on the calculator, we would find that the value of the acceleration is given by 1.46 meters per second square. And why a, not alpha? Because they're asking for the linear. Here, notice that even if they're asking us for the linear, which means at the first glance we need to apply Newton's second law for translation, but what makes us applying again Newton's second law for rotation? Because we have two unknowns given by Ft and A. Always in such type of systems, whenever we need to determine the acceleration for pulleys, we need to apply Newton's second law twice. Sometimes we're doing it for the two objects, and if we have combined motion, we need to do for translation and rotation. Now in part C, we need to determine the angular speed. So first, let's determine the linear speed, then we can find the angular speed via the radius. Now, do we have the value for the radius? Yes, the radius is given by 0.1. Therefore, we can say that because the acceleration is constant, we can use safely kinematics. Then Vx is given by Vx0 plus Axt, starting from rest and upon acceleration of 1 point. I've said that the acceleration is 1.46, then 1.46 multiplied by 3. That would give us a final speed given by 4.38 meters per second, but we're interested in the angular speed. The angular speed is given by v divided by r, which is 4.38 divided by 0.1, which is basically 43.8 radians per second. Now in part D, we need to calculate the increase in total mechanical energy of the disk from t is equal to 0 to t is equal to 3 seconds. Now the increase would be the change in the kinetic energy and the change in the mechanical energy, and we're talking specifically final minus initial, because upon applying this force F, which means that we are injecting energy in the system, energy will appear in two versions. One of them is the speed, which is kinetic, and the other one would be the elevation, which is the increase in gravitational potential energy. So before doing so, let's take the PE level to be the horizontal passing through the center of mass of the disk and the initial position. Then let's say take the PE level to be the horizontal, passing through the center of mass. So take the P level to be the horizontal passing through the center of mass. of the disk in the initial position. Therefore, what is our initial mechanical energy? That is about kinetic and gravitational potential energy. That would be 0 plus 0 is given by 0. Now what's our final kinetic energy? It's given by kinetic energy final plus gravitational potential energy final, and that would be half. The mass of the system is given by m, and the speed that already we have determined is this one. But here pay attention, we have two types of kinetic energy. We have translational and rotation. For this reason we need to add another term which is given by half I omega square, and we have a gravitational potential energy given by mgh. Now we know the value of m, we know the value of v. I is half mr square, we have m and r, we have omega which is 43.8, but we need to determine h, and they told us calculate, which means, and they gave us the values for time, then we need to calculate the numerical value and the increase in the mechanical energy. Now the height can be determined from the following, since we know everything. So y is given by y0 plus vy0t, which is the initial speed, plus half a yt square, starting from the origin with 0 initial speed. Now h, which is the vertical position, would be half. Our acceleration is given by 1.46, and for a time of 3 seconds. Now plugging that on the calculator, we would have that the vertical height elevated by the disk is given by 6.57 meters. And now let's replace all the values. Half, the mass is 2, the speed is 4.38 to the power of 2, plus half, the rotational inertia is half, the mass is 2, the radius is 0.1 to the power of 2, omega is given by 43.8 to the power of 2, plus the mass, which is 2g, is 9.81, and the height is given by 6.57. And plugging that expression on the calculator, we would have that the final mechanical energy is almost given by 158 joules, which means the increase in the mechanical energy is 158 joules. Now in part A, they're telling us the disk is replaced by a hoop of the same mass and radius. So what's the difference between the disk and the hoop? The hoop is more inertial, so more kinetic energy, more rotational kinetic energy would be gained, and less translational kinetic energy would be gained, but in total they would be the same. So we're talking about a greater translational speed, for the hoop, less translational speed but a greater angular speed. Indicate whether linear. Linear, which means would be less than, because we know that hoop is more inertial and less linear quantities would be gained. So let me state, since the rotational inertia of the hoop is greater, for the same mass, and the important thing here to mention that the mass and the radius, they are the same. We cannot say directly that the hoop is more inertial than the disk. This holds true whenever the mass and the radius are the same. So for the same mass and radius, then the linear acceleration would b less than that of the hoop. And that's it for me in this video, guys. See you soon in a new one.